Hi, my name's Gus Gonzalez, and we're going to work on this problem here. We have to find the Maclaurin series for f of x of square root of 1 plus x. Okay. And we can rewrite this as 1 plus x to the 1/2. And for Maclaurin series, it's just, this is the typical format. It's f to the n x all over n factorial x to the n, since it's a Maclaurin series and it's centered at 0. It would be x minus c to the n, but in this case our c is 0, so I'm going to leave it how I had it. Oh, that's fine. So here we're taking derivatives, and we can do this handy little chart right here. So what this is saying is this is the term, this is the derivative, and this is the derivative with 0 plugged in, since it's Maclaurin series. So we're starting with 1 plus x to the 1/2. When you plug in 0, you get 1. Our next term, take the derivative, it's 1/2, 1 plus x. The derivative of the inside is 1, it's negative 1/2. Now when you plug in 1, you get 1/2. Our second term, drop it again, negative 1/4, 1 plus x, this time to the negative 3/2. Plug in 1 and you again get negative 1/4. I'm going to move over here, get our third term, negative, and this was 3/8, 1 plus x to the negative 5 halves, and when we plug in 1, when we plug in 0, we get 3/8. Alright, we'll do one more term. The fourth term, we get negative 15 over 16, 1 plus x to the negative 7/2, and again, we plug in 0 and we get negative 15/16. Okay, now that we have this, let's put this here. Here in the denominator, we can see a pattern of 2 to the n. So we expect this to be somewhere in the denominator. The signs are changing, so we're expecting a negative 1 to some power, alternating signs. And, okay, here's the weird part. The numerators, they change to 1, 1, 1, 3, 15, and then if you do it again, you get 105. This is a very strange pattern, but if you look at it again, it's easier to see if you write it like this. 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7. It's easier to see it like this, but it's still hard to find out what kind of, it looks like a factorial, but what kind of factorial only gives you odd numbers. So after looking at this pattern for quite some time, and lots of researching, I found out that it can be explained by this right here, 2n minus 3 double factorial. So that explains all the odd numbers that are coming out. But the problem with this expression is that our series goes from n equals 0 to infinity. And when you plug in 0, you get negative 3 factorial, which you can't get. So to fix that, it changes to 2n minus 1 double factorial over 2n minus 1. Okay. Now that we've covered this problem with the 0, we can simplify this even more to become 2n factorial all over 2 to the n factorial to n minus 1. And this term describes our numerator. I previously said that the denominator is 2 to the n. So when we divide this by 2 to the n, we get 2 to the n factorial all over 2 to the n times 2 to the n times n factorial times 2n minus 1. Now the 2n's here, they multiply and become 4 to the n. And this is our nth derivative. Well, this just describes the magnitudes. It doesn't describe the sign changes, which is positive, positive, minus, positive, minus, positive. So we can put -1 to the n. Okay, so the -1 to the n would describe it, except that if you plug in n equals 1, you should get a negative value, but we get positive. And the best way to fix that is to change this term right here to, instead of 2n minus 1, we do 1 minus 2n. And that is our nth derivative. So now we want to plug that back in to our Maclaurin series formula here. To the n. Okay, so we plug that back in and we get -1 to the n, 2n factorial, all over 4 to the n factorial, squared, since we have factorial in the series, and an n factorial here, times 1 minus 2n. And this approximates 1 plus x square root. Thank you.